Alright, in this problem we're asked what mass of water is contained in a closed room, and they give us a few parameters. They give us the volume, which is 5 meters times 6 meters times 2.4 meters. That's a total of 72 meters cubed. We're also given the temperature of 25 degrees C, which is equivalent to 298 Kelvin. To convert, we have to do plus 273. And we also have the humidity, the relative humidity, which is the same thing as when they say humidity. Typically, what they mean is the relative humidity, 55%. And we know that the relative humidity is equal to, by definition, the partial pressure divided by the saturated vapor pressure. This is pressure. So partial pressure divided by saturated vapor pressure. The partial pressure is the pressure that water would have in the air if there was only water. The actual pressure that you would measure is higher, and that's because there's not only water molecules, but there's also air molecules like oxygen and nitrogen, and so those will contribute to the pressure. The partial pressure is the pressure if there was only water, and the saturated vapor pressure is the pressure at which there is no more water that can evaporate into the air. So that's when the air is saturated with water. We can get this number from table 13-3, and if we look for a temperature of 25 degrees C, we know that the saturated vapor pressure is 3170 Pascal. So this allows us to isolate partial pressure here by sending the 3170 on the other side of the equation. We have partial pressure, which is actual pressure of water only, to be 55% times, oops, excuse this ugly percentage. Okay, 55% times 3170 Pascal. This is 1744. Right? And we're asked what is the mass of water. So if we have the number of molecules of water, we'll be able to convert to mass. And now that we have volume, temperature, and pressure, we can use the ideal gas law, PV equals nRT, and calculate this N. So N equals PV over RT, and that would be our pressure here, 1744. This is the pressure of water in the air, times our total volume, 72 meters cubed, divided by R, times the temperature, that gives a total number of moles of 50.7. But we want this in terms of kilograms because we want the mass. And so, what is the mass of 50.7 mole of H2O? what is its mass in grams, for example? Well, H is the sum of two H atoms plus one oxygen atom. And so if we if we look for the atomic mass of all of those atoms and sum it up, we will have the molecular weight of one molecule of H2O. So if we look at under the periodic table, we will have the mass given here. So this is 1.00, and it goes on, but we can approximate that it's just 1. The units of this is either 1 mu, which would be the weight of one particle of H, but it is also equivalent to 1 gram per mole. So if you take 1 mole of H, it's going to weigh 1 gram. So we have this twice because there is 2 different hydrogen atoms in H2O. And then we have the same thing for O. If you look at it, you will see it is approximately 16 grams per mole. We could keep more numbers, but we don't need that much accuracy. Summing it up, we have that water is 18 grams per mole. And so by combining 50.7 moles of water and the weight per mole, we see that the mole cancel out, and we are left with weight, which is the total weight of water in the room, and that would be 913 grams. So that's an impressive result, I find. There is almost 1 kilogram of water in the room, like 5 meters by 6 meters by 2.4 meters. This is potentially your kitchen or your bedroom. 1 kilogram of water, if the relative humidity is 55%, of course. But I think this number is, I think 55% is realistic. So there's a lot of water in the air. And that summed it up for this problem, because that was the answer given in the manual.